Well, this is the first lecture for Chapter 2 for ordinary differential equations. And in this chapter, we're going to do second order differential equations, specifically the linear ones. There's a Chapter 3 for nonlinear. And then we're also going to consider systems of two first order equations called planar systems. In this lecture, I'll talk about some of the general definitions and the vocabulary, but I'm also going to talk about a contrast with Chapter 1. Some of the terminology in Chapter 1 is also used with these second order equations and these planar systems, but if you use the same word in a different context, it takes a while to sort that out, and that can slow things up in learning this chapter. So I'm going to try to separate those out right away so that you get the right definition for the terms as they're used in this chapter. So the first thing we're going to talk about are second order differential equations. These are equations that contain the second derivative of the function, in general y, and nothing higher. So you're going to have a second derivative in the equation. And then we have the same types as we had before: homogeneous, non-homogeneous, autonomous, non-autonomous. For review, autonomous has to do with the independent variable t. Autonomous is there's no explicit t dependence, and a non-autonomous t appears explicitly. Like you can even read that. Okay, homogeneous and non-homogeneous. If you take all of the terms involving the y and put them on one side, if it's equal to 0, it's homogeneous. If it's not equal to 0, if it's equal to some function I'll call h of t, that's called a forcing function, then it's non-homogeneous. Linear and nonlinear. In this chapter we're going to do linear equations. And then again we have the initial value problem and boundary value problems. And again we're only going to do initial value problems like we did in Chapter 1. So here's a general form of the second order linear differential equation that we're going to look at here. So you see, and this is standard form, so you see the second derivative as the highest derivative. There's coefficients which may or may not depend on t. In the general form they do depend on t. In the if it's constant coefficients, you don't have a dependence on t. P and q are just constants. And then if it's homogeneous, you have a 0 here. If it's non-homogeneous, you have h of t. H of t is like the forcing function. And we talked about forcing functions before in the method of undetermined coefficients. Now the method of undetermined coefficients will be used again in this chapter. The method of separation of variables and integrating factors, those methods are not used here. Something else to note, a clear screen, in these initial value problems there are two initial values. That's because this is a second order equation. And why do you need two? Well, if you think about it, if you took a derivative of a function, I'll show you, this is obvious too. Say you have some function. And when you take the first derivative, well, you lose one piece of information. I've got at plus 3. Okay, so I need one initial condition to recover that. I take another derivative, and then of course I've lost the second piece of information. Well, this was good planning, wasn't it? Okay, let's just do it up here. This becomes 8. So in this case, now I've lost this information. So that's why I need two initial conditions. Is a two-dimensional problem, you need two initial conditions. And the two initial conditions that we use are the value of the function at some time t0, I put 0 here, and also dy by dt. I had trouble with this word processing at writing this, evaluating this at 0, and that's often called y prime at 0. Remember, in this class we're using prime, hopefully not too many times in these notes, but often in the book the prime can mean a derivative with respect to time. Whereas if you're in engineering or physics, you use the prime to denote derivatives with respect to spatial coordinates, and the dot to mean a derivative with respect to time. But we're using the prime here just to mean the first derivative with respect to time in this case. Now we'll look at the other structure that we're going to consider. This structure will be considered in the second order differential equations themselves will be studied in the first 6 lectures. And then the rest of the lectures in chapter 7 will be on these planar systems. I'm going to go over them both here so you get the vocabulary straight, but they're going to be related, but we're studying them separately. Okay, so here is a planar system. It's a system of 2 equations, and I'm following the notation in the book and using x and y. Now a better way is to go dy1 by dt and then dy2 by dt, because you might have a larger system, and so then you're ready for dy3 by dt, etc. Okay, but we're going to use x and y for the general system. So these 2 equations are related. How are they related? Because the derivative with respect to x is some function of time, x of t, and also of this variable y. And dy by dt is some function, a different function of t, and then of x of t, of the other variable, and then y of t itself. Sometimes they're uncoupled and there's no dependence of the y on x, no dependence of the x on the y, but that's just a special case. This is the general form for the system, a system of first order linear equations. You might say, why are there first order linear equations here when this is a chapter on second order equations? And that's because these systems can be derived from the second order equation. I should have said, or I sort of implied, but I didn't really say it, some systems. The systems do not have to be derived from a second order differential equation, but they can be. So any of these second order differential equations can be rewritten if they're linear at all. You can, okay, so here is the equation for a harmonic oscillator that's the spring in a mass system. So K is Hooke's constant, M is the mass, and beta is some kind of friction or damping coefficient. Now this is a second order equation. Notice that almost everything that involves motion is a second order equation, because, well, you start with F equal ma, or something better. You could try. You've got the time dependence of displacement or the time dependence of momentum. So you've got these second order. You've already got a second derivative when you write Newton's law, and that's why a lot of these, all these ones with motion, end up being second order equations. But now I'm going to take this equation and I'm going to write it as a system. So the system had 2 variables. Remember, there was an x and a y. So I take the s, and I'm going to use that displacement, and then I'm going to use the derivative of the displacement, and what is that? It's velocity. So that's my second variable. So the derivative of displacement equals velocity, and the derivative of velocity, but what is the derivative of velocity? dv by dt is d squared s dt squared. So that's right here, and so that will equal, of course, minus km times s, this term, and this term, minus b, oh, it should have been beta, over m times the velocity. Let me go through that again. So I start with the second order differential equation, and it's in terms of some variable. In this case, it's s of t, but it could be anything. I take its derivative and give it a name. In this case, I'll call it velocity. These are my 2 variables for my system. This one is for the s, and this is for the v. Okay. When I take the derivative of velocity, I'm really taking the second derivative of displacement. So all of this ends up down here. And this first line is just the definition. ds by dt equals velocity. That's my first equation. The second equation is the derivative of velocity with respect to time equals minus k over m times s. That's right here. The s appears here. Minus b over m times v. Why do we use v? Because v is ds by dt. Now these systems can be written or abbreviated in as matrices. Okay, so ds by dt, dv by dt is here in this vector. Here's a solution vector, and here's our coefficients. 0, 1, minus k over m minus b over m, or beta over m. So this is abbreviated even more. We define this vector y as, now you might say this is kind of a confusion. Here we have y here, and then we call it capital Y here, but there's an x inside of it too. And so just get a, you just have to accept it. This is the notation. It's commonly used. It's used in the textbook. Now look, if you'd written this, it would make sense. If instead of calling it x, you called this y1 of t and this y2 of t, then using a capital Y out here would make sense. But they wanted to use the x, and we're kind of half following the book, so that's why it looks a little confusing. Okay, so here's the y. Y is the solution vector. And A is the coefficient matrix. And that's the notation. So here's A, it's really a matrix. Y is the solution vector, and dy by dt, of course, gives us our system. Now for these systems, there are two types of graphs. One of them is a graph of the solutions themselves as functions of time. So we've got these solutions, x of t, y of t. Remember, there were two variables. And plotting those versus time, so here would be your x and your y. Perhaps they're sinusoidal. I'll show that in a minute. Okay, that's a solution. But then what we plot maybe even more frequently is a parametric representation of those solutions, and it is called a phase portrait. So we assume that the x of t and y of t are a parametric representation, and we plot them against each other in the xy plane. So here is where the phase portrait happens, and this is the solution. Okay. Now the direction field is here. This is, I'm going to go through a contrast, but this is the start of the contrast between the first order equations and these systems. The direction field is plotted right here. For the first order solution, the direction field was plotted with the solutions. For the first order equations, the direction field was plotted with the solutions. Here, the direction field is plotted with the phase portrait. So here's an example. We have just some sinusoidal equations here, and those are the solutions of this system. I'm not going to solve it now, just accept that those are the solutions of this system. Right. Here are the solutions plotted as the functions of time. Okay, the x of t, y of t plotted separately. Here is the direction field and the phase portrait, and it's plotted in the xy plane. See the difference here? You can see the direction field here. If you plot these sine and cosines against each other, of course you get a circle, which you studied previously in parametric equations in, I think, calculus 2. So let's finish this contrast between the first order differential equations and the second order differential equations and the planar these 2D planar systems. So we start off the first order equations, and we wanted closed form solutions if we could find them, and we found them by analytic means, and those were separation of variables, integrating using an integrating factor, and undetermined coefficient. Now in this case we also want closed form solutions. It's interesting here that the analytic means is more algebraic. We're not going to use integrating factors. We're not going to use separation of variables. We're going to use actually the quadratic formula quite a bit. And the method of undetermined coefficients will also be used in this chapter, in chapter 2. So in this cases, both cases, we're looking for those closed form solutions. We may not be able to find them, but we're looking for them. Then in the next lecture here, and in the second lecture in the other chapter, we looked at existence and uniqueness theorems and discussed linearity. If you recall, there were two aspects of linearity, one for homogeneous equations, and in that case you had, for the homogeneous equations, there was a principle of superposition. For the non-homogeneous equations, there were two extended principles of linearity. Right. In this chapter, again, we're going to look at existence and uniqueness. Those distinctions hold for linearity, but there's another idea here that didn't occur in the other one, and that's what's called a basis for a two-dimensional space. Not necessarily R2, any two-dimensional space. So that's going to be different, and that will be considered in the next chapter, in the next lecture. Now for first order equations, we needed to find equilibrium solutions. That would be some values of y that set that first derivative to 0. For these two-dimensional planar systems, we need a vector that will set that derivative of that vector to 0. So in other words, we're looking not just for a y equilibrium, but we also have an x and a y, because that's a vector, and those are the components of the vector. Then in the first order system, we went to the YT plane and we do a direction field. And the direction field were little vectors, and the slopes of those are little lines or little vectors, and the slopes of the lines were equal to the value of that first derivative in the differential equation evaluated at that point. We look for isoclines, we look for nullclines, and then we sketch solutions. That all happened in the TY plane. In this chapter, the direction field is not in the TY plane. It's not in the time plane at all. It's in the XY plane. There are structures, there are straight line solutions. We're going to see some of those. But in this direction field, we're going to sketch the phase portrait. And that's a parametric picture of the solutions. That all happens with the direction field in the XY plane. And there is no separate phase line. For the first order equations, there was a separate phase line. Then in the previous chapter, we looked at stability. That's how did the solutions behave with respect to the equilibrium value. Were they approaching it in forward time so that it would be stable? Were they flying away from it in forward time again, so that would be unstable, an unstable equilibrium? Or was it a semi-stable equilibrium? Then we looked at bifurcations. We looked at how those equilibrium values changed and how their stabilities changed as parameters in the differential equation changed. For systems, we again look at stability, but the word stable and unstable, they have similar meaning, but there are additional structures. There are things called saddle sources, sinks. There's spiral sources, spiral sinks, single tangent sources, single tangent sink. So there's a lot more structure here when you come to stability. It's not just those three terms anymore. And for bifurcations, bifurcation is a path in the for the change in the phase portraits. So it's not just a value of the equilibrium that's changing, its stability, it's the whole phase portrait that changes as a parameter changes. Okay, so I just wanted to point this out. I think the most important thing to remember is that when we get to the direction field, we're working in the XY plane, not in the YT plane.